1 second, sir. Now is it okay, sir?
Fine. I just I have shared my screen now.
Acha.
So is my screen is visible, sir?
Yes, sir. It is visible, sir.
Right. See, good afternoon all. So in the earlier sessions, we discussed about the very fundamentals of neural network, and later on we discussed about convolution neural network and its architecture, and the thin difference between a machine learning and deep learning environment, on various different feature engineering tasks we discussed, and followed up by we had a close discussion on different error handling methodologies. With respect to the conventional machine learning or even deep learning environment. So, and in the next class, the topic for today's session is on recurrent neural network. Right. See, basically, we have different categorization or different types of available data we can able to derive with. And one among them is like a time sequence data. So the time sequence data, a sequence data in general, it differs from our the regular structured data what we have. So they are see, for example, a sequence data example can be like a speech, maybe a text, maybe like a weather and climate data, what we would have collected for past a few years, or maybe a sales data of a business, of a product. So those are all sequence data. To handle those sequence data, whatever the regular architecture what we have, or the conventional neural network, the little advanced architecture when compared to our conventional MLP, right, or AI in an artificial neural network, will not be sufficient for that one to handle, because the sequence data it will be varying with respect to time actually. For example, day 1 sales, day 2 sales, day 3 sales will not be same, and it will be varying. And also like there will be a dependency between one data and the next data. For example, if I am talking if I am continuously talking in my speech, there will be a dependency between the first word and the occurrence of the second word. So likewise, the one-to-one, or maybe like there may be a long dependency also. The first word in my sentence and the last word in my sentence may also have a no dependency. Like to uncover all this and manage the seasonality and trend which is available in our data, right? Our regular architecture will not be sufficient. So what people have come out, is a variant architecture that we call it as a recurrent neural network, which will have a recurrent loop. See, for example, in any CNN or our earlier artificial neural network architecture, we will have a input to the model, and based upon the input, the neuron does some computation, and it gives some result. Right at the last output layer, we will be getting some output. So the output what we are getting now is dependent purely on the current input only. So in those architecture, but here we are going to have a recurrent loop which is going to maintain or manage the dependency between the previous input, the previous output of the model, and the current input to the model. So the recurrent loop is nothing but like, if you could able to see the schematic view here. So this is the difference between our regular architecture and the recurrent architecture. In a regular architecture, we will have a set of input neurons, and which is connected to a hidden layer, and the output of the hidden layer 1 will be to the 2 will be sending its output to the output layer, and finally output layer will give the class probabilities. But here, So we will be giving our input to a neuron, and the previous state of the neuron will be applied along with this X through this recurrent loop. And based upon this both input, now we are not giving only one input, we are giving two input now, the previous cell state and as well as the current input now, X and the previous cell state will be the input to the model, and based upon it the model is going to give us an output. See, in our now I think you can able to see my whiteboard here.
Yes, sir.
Yes, so thank you. So in our regular neural architecture, our input, and we'll be getting an output, and if it is X and it is connected through W and it is computing nothing but a weighted sum, so it may be a single layer or multi-layer or whatever it is, this box is going to be our consider it is our set of layers. So output Y, now we can able to relate our Y W transpose X of some activation function, because the output of any neuron we will be applying through an activation function F. So this way we can able to compute, right, our output here in our neural architecture. The thin difference here is so this is our X and this is our some H. So here along with the input, I am going to denote the as it is in time steps, first time, second, every time it is happening, I am going to denote that with xt. Xt is the current time and ht minus 1 is the previous and output now. So y equal to, so this has been connected with the weight WHH, and this has been connected with the weight WXH. So when we want to derive Y, so activation function WHH multiplied by H of t minus 1 plus WXH multiplied by XT. So now what we have done, simple, right? So earlier we had only one input, now that has been replaced with the two inputs. Now, simple, nothing more than that. So now this will become my current cell state HT, and this will become my YT. Like this again, next time what will happen is this will become HT minus 1, and along with the, for example, so YT, whatever we have calculated here, WHH so now what will happen is this will become next time, this is for example time equal to some 6, at time 7th step what will happen is, otherwise what I will mark as T6, this has some T5, H5, and this is as T6. So when we want to calculate Y T7, so this entire WHH multiplied by H T6 plus WXH multiplied by X T7. So now by this one we can able to see that the current output depends upon the previous cell state and as well as the current input. Two things here. So like this way we can able to roll the dependency between the the one input and the next output. So sequentially we can able to manage this dependency. What we were actually discussing. So a recurrent neuron simply differs from our conventional neuron in the way that it stores the state of a previous input and combines with the current input. Thereby it is it is getting the ability to preserve the relationship between the current input and the previous input. That's it. See, for example, now we'll see a small flow of the data within this recurrent neural network. For a basic example, see, likewise we will have a lot of problems that can be solved using a recurrent neural network model, and in one such is like a next word prediction or next character prediction. See, like for example, there will be some intelligence when we start typing in some few editors. Automatically when we start typing in the down, there will be some options for us to select. Instead of fully typing it, we can just opt from it. Like for example, if I start typing H, then the next word it should maybe like I or E, right? Hello or hi. So likewise I can fill that things. So next character prediction, that is the task that we are going to perform now, and we are going to build a model. The aim is to build a model which could be able to predict the next character, and the especially this model is going to be trained only for a word hello alone. HELLO, hello. Before to that, I would like to ask one simple question, like if everybody is comfortable with the working principle of neural network, then we can go ahead with this. Otherwise, if you have any few questions there or some clarification if you need, so we can discuss for 5 to 10 minutes on the neural network topic, and then we can proceed. Because until if you understand how input flow from the first layer to the last layer in a neural network, and if you don't have an idea on that one, understanding this will be a little tough. So I would like to request the participants, like if you have any query on neural network architecture and the flow of input from the first layer to the last layer, right? So if you have any few query, you can please raise now.
Yes, participants, if you have any questions, you can talk to Professor. If you can raise your hand.
Further, if we start discussing this recurrent neural network, and if you don't understand, or if you have some doubts, so both this concept will get confused. So that I want to make sure that the base is ready, and then we can build on top, any advanced concepts on top of it.
Yeah, if anyone has any doubts, you can raise your hand. I'll help you to unmute. Yeah, I think we don't have, I guess, sir.
Okay, thank you, sir. Thank you so much. Right. So now we will see the flow of input for modeling a recurrent neural network to predict the next character for the word hello, right? So in the hello, right, the input here is a text character. We have to convert this into numerical form, and we have to apply as an input to the model. Number one, directly we cannot give this, right? So HRE So we have to convert that into a numerical form. So any word, right, or any text or any speech signal, like we will extract some features. So here in text we will be converting them into numerical form, and we will be giving it as an input to the model. So now in this word hello, there are 4 unique characters are available: H, E, L and O. So these 4 characters will form our dictionary for us, right? So if at for example, if at a time t the input given to the model is E, right, then and the previous input to the model was H, then the model should predict L next, right? So because t minus 1 input was H and t input was E, so that model should predict next as L. And if again L was typed no, the model should be predicting next again and one more L, because H, E, L, L, and then the model should lastly predict O. This is how we have to build the model. Now we will see the output and the input flow. See, as I said, like, so the cell state, right, the neuron cell state, right, it can be estimated using the activation function and the 2 inputs to the model are ht minus 1 and xt, right? So each successive input we call it as an time step here. And in the basic recurrent neural network architecture, the activation function that was used is a tan h activation function. And the tan h activation function output will be ranging between, for example, tan h of some input x can be ranging between -1 to +1. So earlier in sigmoid activation, the output will be ranging between 0 to 1. We know that one. So the weights as denoted, WHH is the recurrent weight and WXH is the input and the hidden layer weight. So we need to calculate the current state, right? HT equal to tan H of WHH multiplied by HT minus 1 plus WXH multiplied by XT. So this we know that. And output Y equal to WHY multiplied by HT, because the output the activation output of the neuron multiplied with the weight will be giving us the YT outputs. Fine. See, now if we see that the 1 hot encoded representation of each of the character, right, is like H is 10001, because the length of the unique character here is 4, right? In our vocabulary we have 4, and to represent the 4 different characters we require one vector of length 4, right? So H is represented as 1000, E is represented as 0100, and O is represented as 0010. Now the initial value of WXH, right? WXH, the matrix size is 3 by 4. The initial values are some randomly chosen, and we have this one. Next one is we need to when we want to calculate HT, for that first we need to find out WXH multiplied by XT, the second term, right? So WXH was this one, and 1 hot encoded representation of H is 1000. So a 3 by 4 matrix multiplied with 4 by 1, we will be getting a 3 by 1 matrix. So that is what the answer, 0.28, 0.90, 0.53, we got it. And then the first term was WHH multiplied by HT minus 1. But when we start our first iteration, HT minus 1 will be 0. There will not be any previous iteration, right? So it will be 0. So WHH multiplied by HT minus 1 will become 0. But our usual formula will be like plus bias is also there, because when we expand this W transpose X, we will be getting Y equal to MX plus B form, right? So where this B is the bias, right? So WHH multiplied by HT minus 1 plus the bias BH, right? So WHH value we know, but HT minus 1 when we multiply it with, we will be getting 0 plus bias value is 0.56. So 0.56 plus this one we will be getting 0.56, 0.56, 0.56. So the WHH multiplied by HT minus 1 plus bias values are 0.56, 0.56, 0.56. Earlier we have calculated the WXH multiplied by XT, that value is 0.28, 0.9, 0.53. So in total we will be getting this value, right? And when we apply tan H to this one, final HT value we calculated it as 0.69, 0.89 and 0.80. I think the flow I'm very clear, I'm making it very clear. If we have any query in this, please let me know. And then next we need to estimate the value of Y, right? So that is our actual output. So overall, right, up to what we have done so far. So WHH multiplied by HT minus 1 plus bias. Sorry. This is like no HT, what we have calculated for the initial input H, right? So when we apply the input H, we have calculated the corresponding HT, right? Now, next T as an input to the model, this HT will become HT minus 1 along with this input E to the model, right? So I think that is clear. So this is HT what we have calculated when we give H as an input to the model. By the time HT minus 1 will be 0. Fine, we have calculated. And then next now I am going to apply E as an input to my model. By this time the previous cell state, right, HT minus 1 will be this one, 0.69, 0.89, 0.80. Now fine. So WHH value is 0.42 multiplied by this 0.698980 plus bias will be giving us this value. The second term WSH multiplied by XT, right? Now XT value is 0100. It is not 1000 because previous input was H. By the time we gave 1000, now the input is E, so 0100, right? So now we are calculating the HT when we are applying E as an input to the model. By the time HT minus 1 value we got from the previous and the current input XT value is 0100. So with all this we are getting these two 3/1 matrices. The sum of it and the tan H when applied to it will be giving us 0.93, 0.94, 0.76. See, this is the cell state when we are applying E as an input to the model now, right? So now this will become HT minus 1 for the next state. So now, for example, at this time when we want to calculate the output, right? See, what output should we get when we apply E as an input? We should be getting L as an output, right? So L corresponding vector representation is 0, 0, 1, 0. This is what we should get. But now when we estimate the Y, we will not be getting this actual 0, 0, 1, 0. We will get some error because we are starting the training now. We are randomly initialized the weight. We have applying the input and we are calculating the output and estimating the error now, right? So now we are calculating Y when we are applying E as an input, right? So WHY is a 4/3 matrix, and then when multiplied with the HT, right, which is 0.93, 0.9476, we will be getting YT as 1.9, 1.13, 0.95, 1.2. But actually what should be the output we should get? We should train the model to give this output 0, 0, 1, 0 because we are expecting L. When we are applying E, the next word we are expecting, sorry, next character we are expecting L. So the model should give output as 0, 0, 1, 0. But model is giving some other. So what we need to do? We have to find the error, and based upon the error we have to tune all this WHY, WHH, WXH, all this we have to tune, and then we have to apply our input one more time and see and make sure that the error is low and we are getting 0, 0, 1, 0 or close to any answer to that one. See, finally YT we will be calculating based upon the softmax, right? For example, this is YT, we will be applying a softmax so that the probability of all this, sorry, final answer is 0.4, 0.1, 0.16, 0.22. But actually what should we should be getting 0, 0, 1, 0 we should get. So this is a schematic view when we unroll the recurrent neural network or unfold the recurrent neural network. So the horizontal line marks the cell state, right? The horizontal flow of line marks the cell state at each time step, and the vertical line from down directed upward will be denoting the inputs at the different time step connected through WXH, and the corresponding output at each time step is marked as Y there. The same one, right? The same, all we know except same, right? Everything is same. What we discussed is, so the output YT depends not only the output at time step T depends not only on the input X but also on the previous cell state HT minus 1. So HT is being calculated based upon HT minus 1 and XT, and still, right, HT plus 1 will depend upon HT. So likewise, thus dependency can be managed here. So normally when we have a neural network, we need some training algorithm, right? And we usually use a back propagation training algorithm, right? By which what we will do, we will estimate the error at the output layer, and based upon the error we will back propagate, and then we will update the previous layer weights, and then we will estimate the last hidden layer. Likewise, we will back propagate the error and we will tune the weights. So here also the same concept, but we will not be back propagating through layers, but we will be back propagating through time, because the error what we got at time step T plus 1, right, will be influenced by HT also, right? Because HT plus 1 depends upon XT plus 1 and as well as HT also. So we have to back propagate through time, and then we have to find out the updates in the weight, updates for the weight. So here also, how do we find out the error, right? Earlier, so we can able to compare two vectors, and then we can able to say like what is the magnitude of the error. But now we will be able to compute the error for each time step, and then we can able to take a average error for a whole time steps. The major problem here is like, for example, the weight update policy for us is like new weight equal to old weight plus change in weight. Again, the change in weight equal to negative of learning rate multiplied by partial derivative of our error function. And when we do partial derivative of our error function, so when we are doing this one, there may be a chance that the derivative value will reach at one point of time, after some successive iteration, will reach to 0, or it will reach to higher values. These are the two probabilities. When it reaches to 0, what will happen? So the gradient term will become 0 or close to 0, right? So W new equal to W old plus 0, nothing will happen. So the model will not learn. The model will stop its learning, right, when the gradient of the gradient reaches to 0 or close to 0. And simultaneously, when it explodes to some higher value, what will happen? Again, our new weight will also reaches to higher, and the next it will continue, and the weight value will be exploding. So these two problems, what we call it as vanishing or exploding gradient problem. When we repeatedly, right, when we apply our sequential input to the model, and when we back propagate the error through time. So by this methodology, the gradient value will either reaches 0 or close to 0, or it will goes higher value. So to avoid this one, right, because when we have to go for many iteration or many sequencing is like when there is a long dependency between our input, right? So now to overcome this issue, vanishing or exploding gradient issue, different solutions are available. One, changing the activation function from our simple tan H into and another activation function called ReLU, rectified linear units, which will be linear. Say, for example, as per this ReLU activation function, for a given input x, the output of the activation function, that is g of x, equal to, will draw on my whiteboard so that it see, for example, output of the output of any neuron we will be applying through an activation function, and then only we will be getting y, right? So in sigmoid, what we have discussed is the output will be floating between 0 to 1. For example, it will be a like, even this is our x input and this is our g of x outputs. So here it can be 0 or it can be 1. Even if our input is 0, when x equal to 0, as per our sigmoidal activation function, g of 0 equal to 1 by 1 plus e to the power minus 0. So e power 0 is 1. So 1 by 2, it is equal to 0.5. So even if our input is 0, output will be 0.5. This is the characteristics of sinusoid. And the tan H, it will be ranging between minus 1 to plus 1. It will be centered on 0. So when input is 0, output will be 0 there. So this is minus 1 and this is plus 1. So even we reach infinity on this end, output will be 1 only. So these two activation functions, right? See, because for example, W old plus change in W will be giving us the W new. This change in W equal to minus alpha multiplied by dou E by dou W. This we know. And again, when we want to expand this dou by dou W of E, E is nothing but 1 by 2. On the day we have seen that 1 by 2 summation of I equal to 1 to M y dash I minus yi whole square. So in this one, this y dash I is nothing but again when we expand it, this is nothing but W transpose X. Sorry. So again it will be keep on expanding, right? So here, when the successive iterations we go, and this derivative will reach at one point of time close to 0. By the time W old plus 0 will no change in the weight. So model will not learn at all. This is why we call that model will stop its learning. The other way what it will happen is when this del W value explodes to very, very higher value, nu will also, W nu weight will also go very higher. So at one point of time it will reach very, very higher value. So to overcome this issue, what we require is an activation function called ReLU. For example, if g of x is the output, it can be x if x is positive, 0 if x less than or 0. So what will happen now? If this is our x and this is g of x, graph goes like this. When our x is positive, the activation function will act linearly, and when your x goes negative, the output will be 0. So linear, our activation function will be linear when x is positive, and the activation function will be non-linear when x is negative, that is the input is negative. So this simple logic, right, redo activation function, it could help us to reduce the vanishing gradient problem. And obviously when our x is positive, right, so g of x will also be positive, right, and when it is multiplied with this alpha, which is a very least value, it will not explode to higher values also. Del w will not explode to higher values also. So we can able to control vanishing gradient and as well as exploding gradient problem through this redo activation function to a limit, right? So this is the advantage of this new activation function that has been adapted in our majority of implementations. So this is the vanishing problem, right? During over the time step, the value of the gradient diminishes, and at one point of time it reaches 0. So when we are having an exploding gradient problem, it can be solved easily using a gradient clipping methodology. So simply what it will happen is thresholding. It is nothing but a thresholding. When the gradient goes beyond this level, then we can limit it off. So any value above t will be considered as t only. Like very simple one, we can able to solve that one. And for solving this vanishing gradient problem, we may use this redo activation function. But still, when we want to manage a very longer dependency between one, for example, in a time series data, I have a daily statistics, and every month quarter, right, will be same. Sorry, every year quarter sales will be same. Like for example, January 1 of this year, our first week of January sales will be same like the previous year's January first week sale. Likewise, the March last week sale will be similar to last year March sales. In this fashion, if we have a data, then for example, the distance between in terms of time steps, the one data and another set of data is around close to around 365 data, right? So now a data which is apart in sequence, I'm saying, right? So one data which is lying in T, which is giving impact to a data which is lying in T plus 365. Then to manage all this longer dependency, the simple recurrent neural architecture is not sufficient, because here in recurrent neural architecture, what we are doing is we are depending upon the previous input, previous cell state and the current input for predicting the current output, right? So likewise, this one-to-one dependency, or maybe like if we increase this window length, like the dependency length, maybe like last 3 time steps we consider, right, and the current input we consider for estimating the current output. If this is the case, then also, right, we cannot be able to manage a very longer dependency like such a one what I have told you. So to overcome this issue, people have come out with a sophisticated architecture called gated, right, architecture, and two variants of those architecture, what we call it as a LSTM and GRU, long, short, term memory recurrent neural network or gated recurrent unit recurrent neural networks. So in this one today we shall discuss about LSTM, right, architecture, which is specifically built for dealing with this vanishing gradient problem. So this is the sigmoid function which I just told you. And no, any query up to this, because it is like a one-way, communication. So keep on delivering lecture is also little boring. So any interaction will be little, helping will help me to give you more content, and it will be beneficiary for other people also. If you have any query, please.
Yeah, participants, if you have any queries, please raise your hand. I'll help you to unmute and you can speak with the speaker.
Okay. So we shall look into the architecture and working principle of this long short term memory. And before into that, there are few categories of problem depending upon the length of the output and input, right? So like one to one, many to one, like for many to many, like different categories for problems are available. We will see that, right? For example, this is an higher level view of recurrent neural network, right? And the flow of data within it. So this is again a drawback, right? If we refer multiple sources for learning, the notations will be slightly varying. For example, earlier we used a notation H and now it is A, right? So both are denoting the same cell state, which is flowing horizontally in our diagram, and the vertical upward line marks our input at different time step, and the the vertical line at the end, at the top, it is denoting the current output from the model, right, at every time step, the same one. So here we spoke about the HT, right, which is calculated HT or AT, here both are same, equal to an activation function. Earlier we saw it as a tan H activation, W HH multiplied by HT minus 1 plus WXH multiplied by XT plus bias. This is what we discussed. Sorry, something went wrong. Right. So and output is equal to activation function of WYH multiplied by HT plus bias, right? So the same everything is being pictorially represented in the down here. And as we said, like we have different category of problem, one to one, one to many. So all this I'll just know. For example, one to one is an example of traditional neural network. Given one input, we will be trying to classify that no input as either some category, right? So the size of input will be one and the output will be one. That's a traditional one. One to many, taking one input, we have to generate a sequence of output, right? For example, music generation. what we will do is we will take the card or the scale what we have to know what in which the music has to generate. So that we will take as one input, and we will generate a sequence of musical notes, right? So that is a one to many, right? That can be done. For example, some people will give the topic, and we have to generate a text related to the topic. Text generation, that is one to many, right? So what we will do is we will train the model on particular topic, right? For example, in sports, and then no, we will say like cricket. Then the model should generate a text which are more related to cricket, right? This is for content development. People have started doing this kind of task actually. For content development, they started using building different machine learning models which could be able to develop sophisticated, high, enriched grammatical content, because when there is a too many vocabulary usage, right? Sorry, when there is a, for example, when we want to use certain high level vocabularies instead of some ordinary vocabulary, we will tend to forget that. But when we train a model, right, to use multiple vocabularies for a particular context or scenario, it will generate with promptly as per the grammar what we train the model, it will generate as such. So one to many in the case of text generation or music generation, right? So will be a model which will accept one input, and then it will be like here if you see that in the notation also we don't have a series of x input, right? Because only one x at the very beginning we will give x, along with that we will generate the corresponding y1, and this y1, right, will be given as an input for predicting this y2. In sequentially we will be predicting it. The cell state will be flowing, that is one to many. And next one is many to one. So many input, right, a sequence input, but output is one. It is like classification. For example, sentiment analysis or sentiment classification, we say this one. On a given text review, we have to say that whether it is a positive or negative review. So input will be a sequence, output will be a only one value, right? So many to many, right? So it is like POS tagging. For example, I'll give different words of a sentence, and correspondingly I will ask the model to say what is the I will ask the model to tag the parts of speech, each and every part of the speech. So for example, whether it is a noun or pronoun, or it is a adverb or what, like every word occurring in the sentence, that we should be in a position to tag it, right? So and one more thing is like in this many to many kind of problem, the length of input and output will be same, because if I have 10 words in a sentence given as an input to the model, the output will be 10, because 10 different tags for each of this word. And there is a second many to many category where the length of input and the length of output will not be same, right? For example, which is called sequence to sequence problem. This kind of many to many, we call it as a sequence to sequence. And in that example is a machine translation. Given input text will be in one language, and the output what we are generating, the text we are generating will be in another language, which is we call it as a machine translation, right? Like what Google is doing now. If you give one text paragraph as an input in English, we can able to translate that into any language. And in this problem, the thing is like the input and output length will not be same. Right. And this is already we have discussed back propagation. We are doing it in time steps. And when we have an text as an input, we already discussed that we have to convert that text input into a numerical form, and the very fundamental methodology is a one-hot encoded representation. But what is the drawback with this one-hot encoded representation is that for example, if I am saying, for example, you are trying to encode the marks, right? You are trying to encode the marks. In that, for example, you have conducted the test for out of 100, and you have all the students' marks in 100, and you are trying to encode it into A, B, C, D, E, 5 different ranges, right? For example, depend if it is above 90 and no 90 to 100, it is A. Likewise, you have different encoding no rule here. Now in this, for example, there are 2 marks for students like 92 and 96. 92 and 96. When we encode, so it will be encoded as A and also A because both are above 90. So what is we need to infer here is in our encoding standards, as the marks are very similar and no the characteristics of the student are similar. For example, they are studying well, they are doing good, they are attending all the classes. Like we can able to do a lot of inferences out of it for both the students, right? So there is a lot of similarity between these two students, and whatever the representation what we have for this marks as A, right, which could able to infer all this, from this representation we could able to infer all these things. For example, if I am representing 92 as A and some 96 as some other S, we couldn't able to derive this conclusion, right? So what we are trying to say is, if we have two different data and if they are very similar, then their encoded representation should also be same or similar. Then only, right, we can say that our representation or encoding is successful. For example, in here one hot encoded representation for different words, maybe like book, soft, teddy bear, right? So they are like 001, 010, 001, like this. We have different representations here, vector representation here. If we say like teddy bear and soft, there is more similarity, there is more connection here. Dependency between soft, teddy bear, and there is a lot. So their representation should also be very close, but we have a very long gap between these two words representation. But there is another methodology, what we call it as word embedding, right? We will discuss in detail about it. And when we follow that approach, word embedding approach, right? So the representations will be very, for example, soft and teddy bear, they are very close, right? So their distance in the, for example, these vectors are the representations in this word embedding format, by which they are having very smaller angular distance here. But a book which is no entirely different from this two, there is no similarity. It is having a very long distance. So that is what we need to infer, like in our representation, in our encoding methodology, the similar words should appear closer than the dissimilar words. So word embedding is a methodology for learning the representation of a text, right? Where the words which are having similar meaning or more similarity will be having a similar representation. So our objective is to build a real value vector for every unique word we have in our vocabulary, right? So our dictionary, right? For example, vocabulary or dictionary is nothing but, for example, you are having one paragraph of text or 100 paragraphs, different articles, right? Maybe like different essays written by different 100 students, and just give me a minute. So our objective is to build a one real value vector for each of the unique word in our vocabulary. Vocabulary is nothing but, for example, we have some different 100, right? Let's say, for example, 100 students are there. Each of the students are writing some essay on a particular topic, right? See, for example, they may be writing different things, right? So each of these text paragraphs cannot be same. For example, they are writing essay on some sports cricket, right? So what I am doing is I'm trying to, with these 100 different text, I am going to develop a model, right? And this model should take all this as an input, and it should able to generate some text output, right? So I'm going to apply all this as an input to the model, and accordingly I'm going to build a model which is going to generate the text output, right? Fine. Text output in the sense, for example, you'll see the given input is also text, output is also text. Now our objective is to convert or represent this text in form of a vectors, and also the constraint is that in this vector representation, the words having, right, similar meaning should be having a closer representation or similar representation, right? Now, what I have to do first task is like, I have to construct a vocabulary or a dictionary. The dictionary here will contain all the unique words that are present, right? All unique words that are present, right? In those 100 different samples, 100 different essays. So I have to collect all those unique, and then I have to build a one dictionary. So what will happen is, for each of these words present in this dictionary only, I'm going to build a one hot encoder representation. For example, in this sports cricket, right? For example, in this SAS, I cannot have a word, right? There will be only some predefined number of no, not predefined. There will be only some finite number of words can be present in it, right? For example, in this one cyberspace, like cyber security kind of words will not appear, right? So I will have only some finite amount of words that will be relevant to the context, right? Will be available for me. So I will compose all them into a one dictionary. So from this corpus of text, we will first we will take no we will derive a set of dictionary or vocabulary, right? So for each of the word present in this vocabulary, we are going to build a one vector representation, a fixed length vector representation for each of this word we are going to build, right? So how we are going to build, we will be seeing that. See, for example, in this one hot encoded, so in this one, no example sentences like "have a good day" and "have a great day," right? So they have some different meaning, right? But if we construct a vocabulary, right, we for all the no for the sentence, the vocabulary will be like "have" is a one word, "a" is another word, "good day," and we have in the second part we have a have already we have included, great is not included, we will include it day. So almost five different unique words we have in these two sentences, sentence 1 and sentence 2, right? From this we have constructed our vocabulary, and now our task is to build a model. That model could be able to generate a one vector representation for this. See, for example, in our one hot encoding, have will be represented as 1000, yeah 0100, good 00100, like. So we have this one, but here what we understood is each of this one hot encoded representation is very different for each of the word present in this vocabulary, even though whether they are similar or no, they are not similar. And also one more thing is like, as the vocabulary size is increasing, the dictionary size when it is increasing beyond a level, for example, I have some 10,000 words in my dictionary, then I cannot use this one hot encoding, because I will represent each of this word with a vector length of 10,000, which is very, very complex, which is very will be sparse also. For example, you have 10,000 words, and in that one word is no have. Then the length of that representation will be 10,000. Only one of that will be 1, rest all will be 0, which is very, very sparse. So this representation will be sparse, and it will make the model computation more complex, and the similarity between the two more similar words we cannot able to retain. These are the drawbacks with this approach, word to vec approach. So for this one, we want to overcome this kind of drawback, we have to build a learned representation model, right? So the learned representation we can able to achieve with the help of two different methodology. One is skipgram and another one is common bag of words model, right? So the schematic view what we are seeing here in the slide is a CBOW model, continuous bag of words. See, for example, here this is also a neural network. This is also a neural network, and just simply, if you compare, right, the two different this architecture with our artificial neural network architecture. So here, as similar, we have an input layer, we have hidden layer, we have output layer, right? The layering is fine, and the input layer neurons are connected to the hidden layer through some weights, and hidden layer neurons are connected to the output layer through some weights. Fine, this is also fine. Our architecture is same. So the only thin difference with respect to our ANN is that output of the hidden layer, when it is applied to the output layer, we will apply it through some activation function, which is a non-linear activation. But here we don't have any activation function at all. That's the first concept, right? First difference. And for example, input layer, right? For example, what we will give is, once we construct the vocabulary, right, for each of the word, we will have some one-hot encoded representation, right? So that we will give it as an input to the model, and we will ask the model to build an output, right, which is of same length or which may be of lesser than that, but a representation that we expect the model, where, for example, I am giving two inputs, two similar inputs. The output vector should be similar, right? For example, if I give first one word, some soft, right? I am getting one y, right? Let we call it as y1, capital Y1, and I am giving a next input word, which is like teddy bear. For that one, I am getting an output y2, right? So there are more similarity between the two inputs what I have given to the model. Then the y1 and y2 what I am getting for each of this input should be more and more similar. They should be very closer. That is what we expect, right? So this common bag of words, right? So we will look into the more details of it, right? Before to that, we will discuss a little about our LSTM architecture, and then we will move on to the embedding, right? We call that as embedding, word embeddings, right? So either this CBOW model or skipgram model, we call that as word embedding, right? So there are two methods are converting the text into numerical vector. One is like using the frequency of the individual vocabulary or plain one-hot encoded representation. We can able to convert that each and every word present in our library into a numerical representation. There are so many drawbacks into that in those approaches. To overcome that, we have follow a learned representation methodology, in which we will have a neural architecture, right? And we will be training that neural architecture to generate a more similar representation for two common words, right? So the next set of things, concept what we will discuss is on LSTM, that is a long short term memory architecture, right? these are all these architectures we call it as gated architecture, right? So these gates within available within each of a neuron, right? So we will be using it for regulating the flow of information, right? So there are two flow of information. One is on the horizontal line, which is like the different cell state at different time step, and the vertical line, which will be denoting the current input, right? So two flow will be there here in each of our recurrent neural network. And what we are going to do is we are going to insert few gates, few like walls, right? Gate wall, what we will use in our pipelines, right? So like that, we are going to use some gates to control the flow of information from one time step to the another time step, right? So we will consider what is this LSTM architecture in detail, and before to that I will show the final one. Yes, this one, this is the final one. Before to that, we have few text things, we will discuss that, right? See, for example, this is our conventional neural architecture. Sorry, that is recurrent neural architecture. So this is the previous state, and this is the current state. Middle one is the next state, right? So for example, when we are applying xt, the current input, the previous cell state ht minus 1 will follow along with this xt, and then it is applied through some tan h for finding out the current cell state ht, right? And which will be flowing to the next step for input along with the xt plus 1. So both of it we use it for computing this next cell state. Likewise, this flow will be there. So instead of having a single neural network layer, right, within every neuron, there will be four, right? We will have four layers here, 1, 2, 3, and 4, right? So what is this role of each of this layer? We will see, right? So the top one is our conventional recurrent neural network, that is a regular, right? Recurrent neural network RNN, and this is the LSTM RNN. Right. So first what I have to do is, for example, to manage a very long-term dependency, right? What we have said is that the horizontal one is the cell state, right? So again, it's small, the cell state here represented as C, right? We have to regulate its flow, right? So how much from this current state should flow into the next state, right? Next time step we have to say, right? So the first layer composed of a sigmoid neural network, right? And a point-wise multiplication. For example, we will see that. So as it is now, there are four layers. We said the first layer is going to be a sigmoid layer. The sigmoid layer, always we know that the output will be ranging between 0 and 1, right? And out of this four, three of the gates are formed with this sigmoid activation, right? So the first step is for the LSTM neuron, right? Specifically one neuron we are discussing now. It has to decide what information that it should throw or forget from the previous cell state, right? So what it should forget from the previous cell state, because the previous cell state, that is t minus 1, is now being carried into t, current state t, right? So now along with this xt, we are applying ht minus 1, and the output what we are expecting is 0 and 1, right? For example, the forget gate output ft, right? The ft is equal to sigmoid function of wf. This function is nothing but our tan h activation function, ht minus 1 xt, because xt and this v2 we are getting plus bias. So the internal calculation is, which is very similar to our earlier discussion, and to that we are applying a sigmoid activation. So this sigmoid decides that, because the output is in the range 0 to 1, if output is 0, it means that completely forget that one, because we are going to multiply this ft with the ct minus 1, which is the previous cell state, right, the previous output of the model. So if its value is 1, then I will be multiplying 1 with the previous cell state. So CT minus whatever, if CT minus 1 is 5, if I multiply it with 1, output will be 1 here. If I multiply 1, right, with this FT, if it is 0.2, then I can able to output only 0.2 here, right? So now what is that we need to infer is this first layer, forget layer, decides how much the model has to forget from the previous state, right? So that will be decided now. Then that is the second layer here, right? So the second layer, what we call it as an input gate layer. So now this layer should decide how much of information that it should accept from the current input, right? For example, so this will decide that how much of information from the current input that we are going to update to the cell state, right? So the previous cell state, the first action what we have taken is from the previous cell state, how much information we have to forget, we have decided. And the next step is from the current input, how much of information that we are going to add into the cell state, that we are going to say using this input gate, right? So here this input, this gate will consist of a sigmoid and a tan H layer, right, and a tan H layer. So the IT is the output of the sigmoid layer and the C dash T is the output of the tan H layer. So I equal to sigmoid of Wi, that is weight, multiplied by Ht minus 1 Ht plus B, because the every neuron's internal operation is very similar, right? Because every neuron is accepting two input Ht minus 1 and Xt. Every layer is accepting Ht minus 1 and Xt plus bias multiplied by the respective weights. Earlier Wf, now Wi, and the Ct is equal to tan H multiplied by Wc, tan H of Wc multiplied by Ht minus 1 Xt plus Bc, right, bias. So now we got this I and the C, product of this I and C plus the C, right? So from this first part, which is hidden here, partially transparent here, we decided how much we have to forget from the previous. For example, Ct minus 1 is being carried, multiply with 0.3. What will happen now? Most of the Ct minus 1 will be forgot now. Ct minus 1 multiplied by 0.3 will get only very few values out of the Ct minus 1 passing the horizontal line, plus the information from the current now, right? Information from the current input, that will be added here, plus. So that will go along with, we have a one more operation, right? So in the next step, right? So first one input layer, next first one forget layer, next it is a input gate layer, and third we had a tan H layer, right? And the last one is again a sigmoid layer, that is this one. So these are all been done, this addition, right? Ct equal to Ft, that is what it is coming, output of this first is sigmoid layer, that is forget gate, right? Multiplied by Ct minus 1 plus this It multiplied by Ct plus here. So now we have this one, the last part now we have to say. Finally, we need to decide what we are going to give as an output, right? So this output will be based on our current cell state, that is your Ct, what we have calculated in the previous step, Ct, right? So that cell state will be sent to a tan H layer and multiply the output to a sigmoid gate, so that we will be outputting the required one, ht equal to this ot multiplied by tan h of ct. So this is the last one, right? So this is the flow of information, right? So this is the way how each and every neuron in this LSTM architecture is deciding how much of information that it should retain from the past, how much of information that it should add from the current input, and how much information it should retain and pass on to the next state. So it all will be decided by these gate values, right? So again these gate values W, right, are the gates, right? So when we vary this W's, respective W's, we can able to change this output. Based upon the error, we will be updating each of the switch in an back propagation through time approach. So this is the working principle, and this is a bidirectional LSTM, right? For example, when we have a backward dependency, we can use this architecture, what we have discussed earlier. When we have a forward dependency, for example, I have a sentence, and in the sentence we have the length of the sentence is close to around some 16 words, and in that I have a word which is occurring in some ninth position, and it has a strong dependency between a word which is occurring at the sixth position and a word which is at some 12th position. So there are two dependency here. One is forward dependency, right, which is the ninth word is depending upon 12th word, and backward dependency is like the ninth word depends upon sixth word, right? So how do we manage this one? So we require a bidirectional LSTM, so which can able to extract the dependency level from the forthcoming data, and as well as it could able to maintain the dependency based upon the previous cell state and the current state. This is another schematic view of it. So I think we have discussed enough about our LSTM and RNN architecture in terms of theory. Next, we need to look into the program executions. That is, we will be having some demo, and then we will move on for discussion. And if till this point is any clarification needs, or if you have any query, please you can raise. Because understanding all this are little dry, I believe, but still, right, at least you could able to infer like, okay, what is happening at least within this layer, and why these architectures are being used, and what is their need. At least you should be in a position to understand this one, and then only a few things can be built on top of it. Even if you further attempt by yourself learning all this or practicing some higher level programming.
Yeah, participants, if you have any doubts, you can raise your hand. I will help you to unmute.
Okay, so I will now share my demo programs, and we will just to see how in program we will be constructing them, and what all the Keras functionalities that are available for building these LSTM model. We will discuss all that. Right. So we will see a quick demo of solving a regression kind of problem on a time series data using the LSTM architecture. We'll see that and how we are handling the data. That will be a little tricky, and we will see that also. And the data what we are going to use is for our demo is airline passenger data for different years, right? Over for different passenger, no, the number of passengers traveled, right, on each of the month was noted down, like from 1949 to 1960 for different year periods, and and every month. So for every year, 12 recordings will be there, and closely 49 to 60 we have 12 years. 12 into 12 we have 144 observations, right? So with this 144 observation, what will be, we are going to predict. For example, up to December 1960 we have predicted. Sorry, we have the data. Maybe what we can do is we can predict for January 1961 what will, because these are all for past data. For example, if we have data from 2000 to 2020, right? 2020 up to this December or November we can able to predict for January, February, March, no, the number of passengers who will be traveling in 2021, right? So no, this is what we call it as forecasting, right? So we are going to just perform a forecasting task on no, on this data, and let's see like whether I have mounted my drive, because the data is available in my drive. So I've been connected now, and I'm mounting my drive. So when we want to run, sorry, mount a drive, giving the permission. Fine. So the drive is mounted now. Now we'll execute each of the code block. So we are going to have maybe like I can little increase the screen size. So this first code block, no, it is going to read the data. So far in our all demo, we used majority of the time we just took the some toy data set which is available in the framework itself. But now we are going to handle a real-time data. So this data we have stored in the form of a CSV file in my Google Drive, and the complete path for it is I have mentioned here. Just a second. sorry sorry for the interruption. Right, so we have that airline data in the form of a comma separated value file, and I have dumped that in my drive, and the whole path for my drive is like this one. And for example, instead of typing this one, people can just expand this. Once after mounting our drive, it will be available in the drive / my drive / within that we can able to find all the folders which are available, and collab notebooks is the file folder, and I have my file here CSV. Just randomly I have named it as CSV. So copy path, you can paste the path. So likewise, instead of typing, we can just get it done from there. So just we are going to visualize the characteristics of the data here. So we are going to read from CSE, and we are going to use the matplot, and we have total 144 values, right? So those 144 values are like this. So we could able to see that there is a trend in our data, right? So the data is it is progressively increasing from year to year, but there is some dip from one month to another month. So this pattern, right, this pattern we should learn, so that what we can do is with this one we can able to predict for what will happen in the further forthcoming days. Likewise, this is what. So the size of our data is 144, 1, right? So there is only one value. So what we have is only for each of the month how many how many passengers have traveled. That is what we have. So the advantage here is like with respect to our indifferent from our conventional neural architecture is that these LSTM networks have memory blocks. These gates, what we consider as a memory blocks, right? So that are connected through layers, right? So a block has component which is making it smarter when compared to our conventional neuron, right? And so that it can able to retain something in its memory, or delete something from memory, or add a new thing into its memory, right? So that is what the cell state is considered as the memory, right? To which from the previous cell state we are forgetting something, we are adding something, and based upon that we are sending something to the next level layer, right? So those are the things, right? Forget, input, output, right? Update and output layers we have. Now what we have to do is we have to right. So we are going to solve this problem, forecasting problem, as a regression problem. In regression, we know that we will be having two data. One is x and y, right? So for a given x1, we will find what is y1, like x2, y2. We will be having this will be our data set xn and yn. Maybe like this will be some 1,000 or 10,000 or 20,000 something samples we will have. This we will take it for training, and we will apply it as input to the model. And once the model is trained, for testing what I will do is I will give x test as an input, and the model what it has to give me is some y test correspondingly will give. This is what the regression problem, right, how we will implement. But in this problem what we have is only we have the x values up to 144 x values we have. Now with this one, what I have to do find out is, I have to find out what will be the X145 or X146. Likewise, I have to forecast for the future, right? Now, how do I am going to rephrase this as a regression problem is, this you consider as X, and Y, I am going to put the values X2, X3, X4. Here we will have X143, here X144. Now I think you understood now. So what I have done is, I took a one lag, right? One lag, that is one shift, and then I have made it as another row here, placed corresponding to. See, for example, based on the month 1, I can able to predict how many customers will be traveling in month 2. Based upon second month, I can able to predict what will happen on month 3. Likewise, I can predict the next month. I have restructured the data in such a way that when X1 is applied as an input, the number of passengers traveled in first month as an input, the model will be trained in a fashion to predict how many passengers will be traveling next month. Likewise, I can rearrange like this also. X1, I can put some X7 also. So this will be like, after 6 months, how many travelers will be there. Rearranging data in this fashion will help me to say, like, based upon the current month, I can able to say, like, after 6 months, how many people will be traveling. So we will have X144 here, and X138, so that we will say what the X144, and after that we will not have data. These data will be removed. So this will 138 data alone we will be taking. I think now this concept is clear. This is 1 month lag and this is 6 month lag. 6 month forehead prediction. This is 1 month ahead prediction. Based upon current month, what will happen in the next month? Based upon current month, what will happen in XT, Y, and Y will be like XT plus 6. So this is what we are going to do now. So before modeling, right, already we discussed that we have to perform few pre-processing tasks, and then one such task is our scaling operation. So as values are in different scale, we have to pull them into a one common scale, right? So we could able to see that the values are like 112, 118, 132, 129, so 178, something like different values we have, even up to some 211, something like very different values we have. So we are going to scale all those value into one range using a min-max scaler. So min-max scaler, already we know the formula also. So after that, we will be splitting the data, right? So 67% of the available data we will take for training, and remaining 33% we will going to take for testing. This can be any percentage, 70, 30, 65, 35. 75, 25. So it depends upon the volume of data what we are having. Just we have only for demo 144 data, right? So 144 samples. So we have taken 96 data now. So when we just see the the train data, it will be scaled to a range 0 to 1 here. Fine. And then no, this is the code block no, that which is going to perform what I have told. Look back, right? So when look back equal to 1, so it will take one lag value and it will be no, appended in parallel with the current value, right? So likewise, this code block will do the task, just shifting of no, the. So maybe like if we say look back equal to some 2 or 3 or whatever, no, the window, right? How many I told like, so for example, in our all our discussion, we said that the current cell state will be calculated based upon the current input xt and the previous cell state ht minus 1. So instead of considering only ht minus 1, we can make the model to consider ht minus 1, t minus 2, t minus 3. That is the window length, look back length. How many look back we should have. So if we give this one, so that we can able to say like, right, no, build up data in such a fashion. So now we have taken this code block and we have constructed the corresponding y values also by taking it. And for model, right, so here we have a shape line x. So it is a vector, right? The train data here for us is a vector. Only one single x values we have, only one feature we have. So when we are applying it to a model, right, like a layer, right, a LSTM or a neural network layer, it is better that if we reshape and add some dummy column to it. For example, number of samples here is 94, comma, time step, right? Time steps are, you know, what we are going is 1, comma, and features like no, the shape here is a 1. So from 94 comma 1 we are going to reshape our no, model into 94 comma 1 comma 1, right? A dummy dimension we are adding so that it will be easy for us to apply and do the vector processing. So now we see that before and after reshaping. So now next task is like constructing the model, right? So we have done the pre-processing task. So here also model is going to be sequential. So here we are going to add a LSTM layer. LSTM says that no, long short-term memory layer and 4 neurons, and input shape is equal to 1 comma look back. At every time step, what will be 1 sample comma look back. How many look back we are going to give is only 1, right? So 1 input comma how many look back. Here it is 1 we have declared. Maybe like if we want to look back 3 or 4, we can give accordingly here, right? So just an LSTM layer consisting for neuron, and then next here dense layer, which is our output layer. So as it is going to be a regression problem, we are going to use mean squared error as the loss function and adaptive momentum as a optimization algorithm for tuning the weights connecting each of the neural units. So then finally we are going to fit the model, right? Same, that is same, train x, train y, because it is supervised learning. Number of epochs, batch size, and the verbose for configuring what will be the output. So we could able to see that the loss is getting reduced from one epoch to another epoch. Even if I run this for one more time, right? So for example, if I want to run 10 more epochs, right? So what I should do is I should run this code alone, because if I run the whole block, what will happen is the model will be freshly created and it will be trained freshly. Now what is happening is from 0.0072 to the 11th epoch 6 to 12th epoch 56. Likewise, the loss is getting reduced, and after 20 epochs, we could able to see that it is reaching some saturation points. If we run for some 10 more epoch, we could able to see that like the model is saturated, Now this is going to be our global minima. We have to stop training the model. And now, right, to make some predictions out of it, right? So for example, to the model, trained model, I am applying the trained X itself, right? The train X itself. And to the model again, I am applying a new unknown data test mode, which I have know the 30% of the data, 37% of the data what we have splitted from our original data set. And now as we have performed the scaling operation, right, to go back to our original units, we have to do the inverse scaling here. So inverse scaling of for the both the predictions, we are doing it and we are calculating the error in our prediction. So when we do it, so for the training data, the error is less obvious, and for the test data, the error is slightly higher. We could able to see that. We should be reducing, right? The test error slightly it should be reduced. So for reducing this one, either what we have to do is we have to increase the number of units here, or the number of epochs, or the batch size. We slightly vary the hyperparameters of the model, and we will see like whether the model is fitting good or not. Now the averagely it is performing, and now this is a plot now. So here what we are going to plot is the original 144 data will be one waveform, and the next what we are going to plot is the predictions for the training data, that is for the first 96, and the prediction for the remaining test data, right, that from the model. So the orange one is the, we'll see here. So the blue one is the, right, our original data, and the orange one is the predictions of the model on the training data, so that we could able to see that the difference between the blue and the orange one is very low, right? And the green one is the predictions of the model on the test set, right? So we could able to see that the difference of is little higher here. But anyway, we could able to see that the model has captured the trend and seasonality in the data, right? So for example, as both are in decreasing, so same it is decreasing. When it is increasing, it is also increasing. So model has learned, right, to perfectly to uncover the pattern which is available in our time series data. Here, we cannot shuffle the data before applying to it, because then the series will get disturbed. Then the dependency between one data and the other data cannot be maintained, right? So we cannot shuffle the data. So next, what we can experiment is by varying the look back, we could able to see that whether there is an improvement in the data or not, right? So when we vary the look back, what will happen? The model will some error. Okay, fine. So we have to completely specify the path. So I have mentioned only the CSV. So the complete path information for the data. Same code, nothing changed, but just a value for this look back we have increased. So this look back we have kept as 3 here. So our x comma ht minus 1, ht minus 2, ht minus 3. So the previous 3 inputs we will consider. So what will happen when we consider all this, right? We will see whether there is an improvement in the performance of the model. Slightly there is an improvement in the test score, right? So nothing much improvement. Right. So there are two different way of implementing an LSTM network. One is as stateful, and another one is a stateless. Right. So here also we are doing training in batches. Right. So when we want the model to pass the trained information from one batch to the another batch, right? Then we call it as a stateful model, right? Then we want the model to forget whatever it has trained for a batch, and it has to start freshly for the next batch of input. Then we call it as a stateless model, right? So a stateful model will have the capacity to remember across long sequences of input, right? See, if we believe that we have a sequence data and across batches of data, we have segmented our sequence into some small batches, and we believe that there is a dependency between the input available in batch 1 and the input available in batch 2. If that is the case, so there is a long dependency line here. So in this case, what we need to do is we have to use the stateful, so that the model training from one batch will be relayed on to the next batch training, right? But in a stateless model, every individual batch will be considered separate, right? So if we believe that there is no dependency of the data lying in one batch and with respect to the other batch, then we can use a stateless model, right? So that will be sufficient. So that can also be specified here in simple when we construct our model just by an argument stateful equal to true. And we can exclusively specify not to shuffle our data. So these are some improvisations that can be done on top of our existing simple plain LSTM architecture, so that we could be able to improvise the results. See, as it is a toy data set, right? So we couldn't able to infer more and comparisons. See, we cannot generalize with this that the stateful, when we go always test scores will be less. So we cannot say that. It always depends upon the data here, right? So here we have batch size. By just selecting another batch size, maybe like we can able to say analyze whether there is an impact on. See, here the batch size is very low. We have divided the batch size 1, and also we have only a very less number of data, right? So maybe like I will increase the batch size into some 12, because we have 96 data. So what will happen now, we will see. Okay, some error records. Also made a mistake. So now we have seen a very three variants here, right? One plain LSTM model, and another one is to maintain a window for look back, and the third one is stateful and stateless one. So on a numerical data, we have seen a demo. Next we will discuss about in detail about the vector representations. So before to that, if you have any queries, I would like to request the participants to post any query. See, again, it is a request, right? So that things can be done further better. Is anyone is practicing recurrent neural network here or some other higher advanced neural architectures for your experiments? Or someone is dealing with some text data here? Fine. See, and the same kind of architecture, right? But for a different task, we will now see. Um, we will take a text data set and then we will perform a sentiment classification on it. And the text data, what we are going to take, it is going to be an movie review data set, which is available as IMDb review data set, right, within the Keras package itself. So here in this, we will have some close to 25,000 movie reviews, right? So each of the movie review will be either classified as positive or negative review, right? So what they have done is already, as it is in text form, right? So they have already done a pre-processing task, and they have encoded each of this text as a some numerical indexes, right? For example, based upon the overall frequency of text words, that is words in the data set, right? So for example, a word will be encoded as 3 if
We
it is.
raise a hand from one
Sir?
madam here. We had a raised hand from one
Yeah,
madam.
please, sir. Please, sir. I didn't notice it.
Yeah, 1 second. Madam, you can unmute. Gurnur Kaur. Madam, you can unmute and speak. Yes, madam. Hello. I think she has some issue, I guess.
Okay, sir. Maybe like if she can, if she rise next time.
Yeah, if she raises hand again,
Yeah, sure, sir. Sure.
I can help her. Okay.
Right. So, for example, no, well, a word will be encoded as 3 if it is the third most frequently occurring word in that no data. Entire 25,000 reviews, right? Based upon the frequency of the words, each of the word will be indexed here, right? So, for example, what they will do is uh, all these 25,000 reviews, across all those 25,000 reviews, what are all the unique words present? First, they will take out. Next, for each of this unique word, the frequency, right, the number of occurrences will be calculated. Done. Once it has been done, then based upon the frequency, right, it will be sorted. The higher frequency first, next frequency, like so. Based, it will be like no descending order, sorting all the words based upon its frequency in descending order. Then it will be encoded like the order in which it is appearing, right? In the sorted order, it is ranking, right? 1 2 3 4 up to some n unique words we will have. So it will be encoded with those rank itself. This is what a simple method for converting a text into a numerical representation they have. But this is not the actual representation. They have encoded, right? They have encoded. Now what we have to do is, so the similar words we have to give a common representation, right? Similar. So we are going to use some functionality, and we are going to extract that database. For example, here we have maximum futures, max length, batch size. We will see what we know, why we need all this arguments. For example, IMDb is the data set, dot load data is the function, and to which we are passing num words equal to max features, right? For example, here what we have taken is 1000. So which says that the words which are in the order like the frequency, the first 1000, right? The first 1000 frequently occurring words from the review alone we are going to take, right? So what will happen to the rest? For example, if a review contains a less frequent word, right, what will happen to the word? For example, we are going to take all the reviews, but here what we are fixing is we are taking only the words which are occurring most frequently. That too, first 1000 most frequently words we are taking. What will happen? For example, I am writing a text like it is so what has been done is we have reviews. So sorry, we have review R1, R2 up to R25K. We have 25,000. So this review will have some set of sentences are like word 1, word 2 up to some word yes, length yes. And this review will have some other set of words. Here I will mark it as something like it will be of not same length. It will be for some other length, some right. So now what people have earlier done is considering now let us consider this R1 alone. So each of this text word they have encoded into a one numerical number, something like some n1, n10, something like some number numerical form they have encoded. So this number, how do they have come out is, so across all this they will take a unique words and then they will construct a dictionary. And this dictionary, right, they, for each of the word they will find the frequency. And once they have the frequency for each of these words, right, they will start ascending order. And whatever the rank it comes, right, that is nothing but here n1 or n10. These are the rank in the sorted order. This is the data set what they have. Now what we are taking is, for example, this is right for, let's consider the first review alone. R1, W1 up to some W S, each of which is like some 110, 1020, 250, 980, something like difference will be there. Now what I am saying is max equal to 1000 I am fixing. I want only words, right, topping the order first, that is first 1000 frequent words. So now when I am reading this R1, fine, 110 word, this will appear. But what will happen to this word which is having a frequency rank of 1250? This will be replaced with some dummy character. Then this is 950. Okay, this will be taken W3. W3. So likewise, only the words that is right falling within this rank, that is falling within this 1000 will be taken, and rest all will be skipped, right, with or replaced with some dummy. I think now it is clear. So what I know mean what we trying to infer is we are taking the review sentences with the highly frequent words what people will use. See, for example, when we write a review for a movie, we will say like mostly we will say like utter flop, boring, like some repetitive, frequently occurring words will be there, which will convey more information to us rather than the very less frequent words, right? So that we are trying to take out, and no less frequent words are not required for us. This is a one kind of feature engineering what we are doing here, right? So from this we have read, and the data, X train and Y train, X test and Y test correspondingly we have taken. Those are the training sequences. Each of the sequence will be of different length. Each of the sequences will be of different length. Why? Because every review will not be of same length, right? So I am writing in some 10 sentences, some other people will be writing in some 8 sentences, some people will write in one sentence, right? So now next thing is like to arrange them into a same uniform length, right? That's the next task here. So for that one, what we are doing is pad sequences, right? So x train comma max length equal to this one. So next one, max length what we have fixed as 80, right? So if it is less than 80, right, so it will be filled with some padding value, some common unknown values, right? So x test likewise here also max length 80, that will be padded. Now if you see that after padding, all our samples will be of a size 80. It will be padded with some zeros, which will not give any impact to our learning. Before cell, I think we have forgot to execute. Yes, this one we have not executed. So we have downloaded, padded, fine. So if we see one training data sample, it will look like this. So 125, 68, right? So these are the some replaced one, two, right? 2 is an unknown, right? So we less frequent words we take it as considered as unknowns, right? And 15, right? This 15 meaning that so in the list it is the most frequent, right? 15th most frequent word, right? 349th frequent word, like this. This is another sample, right? So the sample, each of the sample length will be 80. Okay, so this is a visual, for example, what we have done is every word, right, from text form we have converted into index, and now if we want to see from index to word, right, so this block we will build, right, and then just and decode it, right, from encoded version to the actual text here. See the 2 what we have marked are nothing but the unknown one, right? So those are here unknown, it has been seen. Plot the characters are very interesting in their own way, and the fact that the book, something like it's going. And the next. So this is for just visual, right? So this is not going to have any impact. So next we have embeddings here, right? So this will go very lengthy one. So this is all we have discussed, right? One hot encoded representation, drawback of it, right? So and the prediction based method, that is not, sorry, the prediction based methods are nothing but our CBOW and a skip-gram model, right? Which use the neural architectures here, right? Likewise. So this one we have discussed. So the difference is that now in with respect to our artificial neural network, here input layer and output layer will be there, right? So the what we are giving is one hot encoded representation of a word we are giving, and we are taking a vector representation, right, from our network here. And this network, the thin difference is that we don't use any activation function here. It is linear, right? So every input layer neuron will be connected to a hidden layer neuron through some weights, right? We will not have any activation here to make the model non-linear. So this model is a very plain linear model. So now this is like right a slight no, for example, this model, what we are saying is, for example, when we give a one hot encoded representation of the first word, the model can able to predict say what will be the representation for the next word, right? Context word. That is one context. And here we can say like based upon last three words, right, what will be the fourth word, we can able to say like this. So input here is three consecutive word representation, 3 or 4 or 5 or anything we can give, right? And based upon that we can able to get an prediction for the next word, right? So we can able to architect such a way also. So here this is multi-context word, right? Multi-context word. So the window length we can fix it. So this is the skip-gram model, right? Next one, actually a schematic view of it, I think I don't have. Right. So compared to the CBOW, it has the same topology, right? But it just no, there is a flip actually, right? So here, in the previous CBOW, based upon a certain context words, right, we will be predicting what will be the next word, right? So now here, right, we will be giving input as one word, and we will predict what will be the context words, right? The words which will come previous or next to this current word, right? So that we can able to predict, right, based upon the current word here, right? So the skip-gram model will help us to predict the context given a word, right? CBOW model will help us to predict based upon a context what will come next, right? So they are playing football, and the goal, something like next what will happen come, like no, we can able to predict based upon all these words, previous words, in the with the help of CBOW. Right. So here for building the model, right, we will continue the sentiment analysis problem, right? So we have taken the data, right, and now next day task is to build the model, right? So here we will have an embedding layer. So that's why I just wanted to introduce some the embedding task actually. Here we are saying like max features, the size is 1000, comma, so here we have an LSTM layer which has 16 neural units, and we have a dropout, right? So here we will have two dropout. One is the dropout between the input and the hidden layer, and the dropout between the recurrent on the recurrent layer itself. So what will be the probability of dropout on the each of that one? We are giving specifying the probability here to manage the overfitting issue, and finally we are getting a one dense layer output, because here we want to say like whether it is a positive or negative review, right? It's a binary classification here. A sigmoid activation can also be used, right? So both sigmoid and softmax will give here same answer, right? So the output of the one neuron here will be equal to probability of given for a given x, probability that y equal to 1, right? So if the probability of y equal to 1 is more than 50, right, then we will consider as a positive review. If the probability of y equal to 1 is less than 50, we can consider it as negative, right? So we can threshold and then we can convert it in any way. So this is the model summary, and we can able to train the model, right, as it is going to be used as a classification one. So binary cross entropy, optimizer is Adam, and here matrix is accuracy, and here loss function is binary cross entropy, right, since it is a classification problem. So if it is a regression, last case what we have done is we have used RMSE as a no loss function. And verbose we have not specified, but still. So now once after all the training process, right, the accuracy of the model is close to 73%, and the test accuracy is 81%. It's a good, fair enough, because we have introduced the dropout. Now what you can experiment is without dropout, what will happen, right, whether there is an impact on the accuracy. So that I request the participants to analyze, and also, right, we can evaluate, right. So which will be like 80, close to 81 we will be getting, because the test already we have given during the training itself, because here at the time of training we have specified validation data equal to x test. Usually what we will do is we will take a part of the trained data and we will apply it here, that is x value we can keep it as, and then we will give it, but as it's a very small data set we have given the x test. And prediction for one particular sample, right, the prediction is 88%. It is saying that 88% it is positive, so test label is positive 1. So we have seen a demo, right, for both text input and numerical input, and we have seen uh, the architecture of recurrent neural network, and also the working principle of an gated architecture, especially LSTM architecture, and a few word embedding techniques we discussed, but not in detail, but still we have discussed. So from now here, I would like to request the participants to raise any question. From there, we will continue. So whatever I was prepared, what I was
participants. Yeah, please, sir. Yeah, participants, if you have any doubts, you can raise your hand. I'll help you to unmute. Yeah, I guess they are fine with the concept, I guess, sir.
Sir?
I think they are fine with the concept, I guess.
Fine. So, okay. So now we'll discuss a little in detail about this, right? Word embedding, right? See, as we said that no, there are two basic category of no word embedding methodology. One is by frequency based mode, and another one is a prediction based. The prediction based is nothing but our model based one, right? So what we have to do is we have to convert a given text input representation into a vector representation, right? So objective is that in the vector representation, the similar word should be more closer enough, right? That is one. So in the first frequency based mode, right? So we have three techniques. One is count vector, and another one is TFD IDF, right? That is nothing but term frequency, right? An inverse document frequency, and another one is a co-occurrence vector, right? So we will see in detail about each of these methods, right? These are very fundamental methods, right? So we will see about them and what are all their drawbacks also we will discuss. So the first one is a count vector, right? So now based upon this, right, we will see how we are going to transform a set of text documents what we will have, and then how to process it further we'll see. See, considering that we have some set of documents, and in all those documents we have n unique words, right? So and then we form that as a one dictionary or corpus or vocabulary we call it as. So for example, so we have D documents, right? And in each of this no document, what we are going to do is we are going to represent, right, each of these words, right? For example, let me use my whiteboard so that it will be easy for people to understand. So D1, D2 up to some D 100. Now in all this one, I have few text, and each of the word, what I am going to do is I am going to so in already what we have done is we have constructed our dictionary, right? So the dictionary is nothing but set of all our unique words, like word 1 in my dictionary, word 2 in my dictionary, and up to my word n. The number of unique words appearing in my dictionary is n, right? So I have 100 documents with me now. So as per this count vector technique, what we will be doing is word 1, how many times appearing in document 1? Let's say for example 10. Word 2 appearing in document 1. So let's say for example 18 times. Like word 3, some 21 time. Word 4, so it is appearing only 5 times. So likewise, we will mark, so we will just have some numerical number saying the frequency of each of this unique word in the document 1. Let's say maybe like this. If it is not if it is not appearing at all, it may be 0. It may be 0 also, right? Maybe 10, something like for the document 2, 3. So if we have 100 document, right, each of this document unique word count we have put it as one row vector. So the size will be now 100 by n. So this is a one kind of representation. So all the documents whatever I have converted that into a one vector, matrices of size 100 by n. So this n is nothing but the number of unique words what we have. So this kind of methodology where we will follow is like when we want to devise a model for topic modeling, right? So at the time we can use this kind of count vector because the most frequent words will be related to a particular topic. As we discussed cricket, it will have certain words. If I write a political documents, if I collect, that will have certain other highly frequent words occurring. If we have some medical documents in that, so depending upon those frequent words, right, and their count, we can able to categorize the documents, right, whether it is this kind of document or what. See, for example, there are certain words which are related to sports, right? So, and if those words are frequently appearing in the document, then we can say classify that, okay, this is a sports document. Likewise, for topic modeling, right, we can able to use this kind of representation. But the problem is that when there are more number of unique words, right, then, and also I have a large volume of documents, then the size of this representation itself will be a very high dimensional one, right? So that makes the further analysis too complex. So this is the first method one. So based upon the count vector. See, for example, what I said is same here. So he, she, for example, we have two sentences, right? So, I think I will come back to my PowerPoint. So not PowerPoint, to my notebook, so that it will be easy. So we have two sentences here. One is he is a lazy boy, she is a lazy boy, and the second one is a Neeraj is a lazy person, something like that, right? So of all this one, the unique words what we have is he, she, lazy, boy, Neeraj, person. So we can skip off the most frequent common words like is, was, all the pronouns and all the most commonly occurring terms that we can skip off, the prepositions, all that we can skip off, only the words we can take it up. So maybe like sometimes pronouns we can include to decide on the gender, right? Maybe like we can retain the pronouns. So here the D, right, the count, the number of samples is equal to 2 and the number of unique words n is 6 here. So the vector representation will be of size 2 by 6. So this is like how many times it is appearing, right? So if it is not appearing at all, it will be 0. So for example, instead of here filling the frequency, we can also fill that with 0 or 1. If it is present, 1. If it is absent in the document, 0. That can also be represented. So it will be like a very, sometimes it will make us a very sparse representation also, right? So otherwise, both can be used, right? So either frequency or the frequency or the count can be used, or it can be like if it is present at least once, we can make it mark it as 1. If it is not available in the document, then it can be 0. That's one method. The second one is a term frequency and inverse document frequency, right? See, for example, what we need to do here is some most commonly occurring word that has to be given less important. For example, instead of removing those e's, was, all words, all those are present, and I am just taking a frequency count. So those will be appearing in all the documents, right? Across all the documents, they will be appearing. But only certain words, right, very specific words will be appearing less, but very specific to the document. So those words I have to give more important. For example, the given example here is like if we have a document which is on Messi, right, a football player, right. So when I'm just representing that word Messi for the document, so I have to give little more importance to it. So for that only this TF-IDS mechanism, in what way it is helping, we will see, right? See, we have two documents here, right? So there are set of terms are available and their counts are given here. This is about Messi, this is about TF-IDF. We have two documents here, right? So the term frequency, right? For example, term frequency says that out of these many words, terms appearing in the document, right? What is the frequency of that particular term here? TF is equal to number of times a particular word appearing in the document divided by the number of terms available in the document. For example, TF of this comma D1, right, is equal to, this is appearing only one time, so 1 divided by total number of terms here is 8, so 1 by 8. So this comma document 2, right, it is 1 by 5. See, with this one we cannot able to differentiate. For example, if we take Messi, right, Messi TF value is 4 by 8.5 for this document 1. So for this document 2 it is 0. So words that are relevant to the particular document will be occurring more, right? Will be occurring more in that particular document only, and they should be given more weightage, right? So here a document about Messi is obviously containing more times, right? The particular word Messi. So what we are trying to do is we are calculating the inverse document frequency, right? But now what is this says is, this IDF is a metric. It is a log of n by n. N, capital N, is nothing but the total number of documents what we have, and n is the number of documents that particular term is appearing. For example, here capital N is 2 and small n for the word Messi is only 1, right? 2 by 1, log of 2 by 1. So for example, for this is log of 2 by 2, so it is 0. So it is carrying nothing weightage. But still, if I now calculate the IDF for Messi 2 by 1, log of 2 by 1.30. So TF IDF, when we calculate for this, for the document 1, it is 1 by 8 multiplied by the IDF, right? TDF multiplied by IDF, 1 by 8 multiplied by 0, it is 0, right? TDF IDF for this, that particular word, this, for the second document is 1 by 5 multiplied by 0, because the IDF value for that word, this is 0, this carries less weightage. But when we calculate for this Messi, we are getting some weightage 0.15. So what this method is trying to do is, this method penalizes the more commonly occurring words, but gives weightage to the relevant words to a document. So important keywords, if we have to classify a particular document based upon certain keywords, right? So which will appear no, particularly in a set of documents. Then we can use this TF-IDF as a measure. So apart from this, again, no, we have one more methodology called co-occurrence matrix, which will have a fixed context window. See, for example, we have a no sentence, and in that this is my no focus word fox, and my context size is 2. So previous to this particular word and after this word, right? 2, the quick brown and jump over. This is my entire context now, right? So we have to find out a matrix. What it will say is that, so if I consider fox and if I take brown, so within this context, how many times it is appearing, right? So the brown appearing how many times within the context of fox, that we have to calculate. Likewise, jump, how many times it is occurring for over. Lazy, how many times it is occurring for dog. Likewise, we have to calculate the context dependencies here, right? So, for example, when we take the lazy word and no, intelligent, so they will not occur together in the context, right? So it will be 0. Lazy and smart will never occur together, right? In sequence, it will never appear. So, but intelligent and no, he, it is more related, right? He is intelligent, he is smart, something like it is appearing in the context he. So, what here we are trying to uncover is the context dependency we are trying to uncover with this, right? So, when we have a fixed window length, right, each of the word, so we will be sliding the fixed window, and we will see like each of the word appearing how many times within this context of other. So that is less utilized methodology because no, extracting the information itself for a very large, huge data is too tedious. So this is again, no, we have discussed a very long, no, lot many times CBOW. So first, when we have a no corpus, we will mark that into a one hot encoded representation. So this is K, this is sample corpus using only one context word. These are all the no, unique words that we have constructed in our vocabulary. For example, okay. So our corpus is no entire like, hey, this is a sample corpus using only one context word, something like. So now out of this one sentence, no, the unique words what we have constructed is this one. So when we want to represent for the data point 4 here, data point 4 is nothing but, so for example, the CBOW we said that when we give one input word, based upon that it will predict what will come next, right? So for example, when we give input as hey, it has to say like what will be the representation for no, this is going to be the output. So when we say this, hey, right, it is like when we give hey, it should predict this. When we give this, it should predict hey and as well as is also, because the previous and as well as next dependency. For example, if we give corpus, it should have the ability to predict sample and also using, right? So the previous word and the next word. So that's why, so when we give corpus here sample and corpus using the previous word, it should also able to predict, and the next word also it should be able to predict. So that is why we are constructing a supervised network here, right? So for example, context here. when we give context here, it should be able to predict one and as well as word also, right? So for example, context one, context word, right? So here, no, the representation for our input here when we give context is 0, 0, 0, 0, 0, 0, 1, 0. And what is the no output? What we expect is 0, 0, 0, 0, 0, 0, 1, 0, 0, something like, right? So this is what we are expecting the model to give the output, right? So for this one, we have tuned a model which will have an input layer. The number of neuron in the input layer will be V and the number of neuron in the output layer will be V, right? Because the length of the one-not encoded representation is V, right? So this CBO model, what it will do is it will accept, right, one word and it will predict, it will be predicting the either the previous or the next word it can able to predict. Right. See, any we will have some objective, right? Any neural network will have an objective. So, for example, in case of a regression problem, the objective of a multi-layer perceptron model or an artificial neural network in general is to minimize a squared error, right? But here, for the CBOW, the objective is to negative log likelihood of a word, right? How we calculate the negative log likelihood, right? So for example, we are going to give certain input words, right? Either one or multiple, right? One or multiple words as an input to the model. With that, it has to predict what will be the next word, right? So equal to the probability of giving an output for a given set of input is equal to exponential of this V is a vector representation of the word, right? Transpose output word multiplied by vector representation of the input word divided by sum of exponential of vector representation of that particular word multiplied by all the input words, right? So this is the way we calculate the negative log likelihood, right? And this is the objective of our CBOW, right? So how do we update the weights? All are same, right? So the two difference here is in the architecture we don't have activation, and the objective function is here it is varying. That's the difference between our ANN and this CBOW. So the disadvantage, it takes the average of the context word, right? Because here, we are seeing that it is taking an average. We are taking a sum and average, right? So it is taking an average of all the context word to determine a particular next word. For example, if we have a word like apple, right? So it may be a fruit or it may be a company. That cannot be differentiated with this CBOW, right? The context, right? That cannot be differentiated with this one. Maybe like if we have not optimized the weights, right? The CBOW will fail sometime. These are the drawbacks of it. So to overcome this, right, we have an skipgram model, right? So what it will do, topologically it is no, structurally it is same as our CBOW, but the thin difference is that predict a context word, right? Given a context, right? The surrounding words will be given. We have to predict the word, right? That is the previous case, right? But now, given a word, we have to predict the surrounding words, right? So that is the aim of the skipgram model. So apart from that, rest of all the functionalities will be same. So maybe like I will be sharing all the 3 days notebooks to the organizing team, and maybe like there are other recurrent neural layers are there. So we have seen about LSTM, and the very parallel architecture is a GRU, gated recurrent unit, and simple RNN we have seen, right, that is very same, and we can able to combine this LSTM with the convolution neural network, so that some better features can be extracted. We can use a 1D convolution in combination with this LSTM, right? So it is always not mean that a convolution neural network we can use it only for images. We may use it for this kind of sequence data also, and as well as for speech. Especially this kind of architecture will be more suitable when we process speech. No, earlier in speech researchers, people have used a hidden Markov model, right? Other Gaussian mixture model for feature extraction and other tasks. But now, with the help of this kind of RNN architecture, we can able to even handle those a continuous speech data also. So these are all the best advantages of this architecture, and I would like to conclude my lecture with this note. If you have any specific queries, we will take. Otherwise, we can wind up the session.
Yeah, so participants, if you have any doubts or any queries, you can talk to the raise your hand so that I'll help. So as sir told, so we will be sharing all the necessary materials with you. So I think my team also has shared the same in the Google Classroom, and they have shared with the WhatsApp also. If anything is required, you can get back to us so that we'll help you out. So thank you, sir. Thank you for your patience and kind knowledge sharing. Thank you very much, sir. So
Thank you, sir. Thank you.
I
Thanks for
think
the
we'll
opportunity.
wind up the session if you are fine. Yeah. Thank you, sir. Thank you, sir. So participants, I think the formalities will be again